Welcome back, everyone, to Medicine in the Moment. So, today we're going to be talking about machine learning, just giving a brief introduction to it with some examples and an overview of how it works. So, first, let's start with some examples, some very famous ones that you probably come face to face with on a daily basis. How many of you watch Netflix? Well, actually, the way Netflix recommends movies to you, based on what you've previously watched and what it thinks your interests are, is based on machine learning. Another one is Siri on your iPhone. Ever since iOS 5, Siri, or as it's officially known by Apple, cognitive assistant that learns and organizes, has been an integral part of every iPhone produced. And finally, we have Google Maps, which a lot of us probably use for navigation every day. In 2017, Google launched a new feature in Google Maps, which allowed the app's users to determine the workload of parking in any given location. They did this based on previous data, correlating the difficulty of parking to how long it took drivers to park. So for those of us who suck at parking, machine learning helped create a very helpful tool. And how we talked about artificial intelligence in the last video, many of those healthcare-specific applications were created using machine learning as well. Now I want to give a basic definition of what machine learning is. The term machine learning was coined in 1959 by American AI pioneer Arthur Samuel. Arthur Samuel was very famous in the field of computer gaming, actually. He designed the first computer program that could play checkers against a human opponent. So after doing this, Arthur Samuel tried to put what he had just accomplished into words, and he called the process machine learning, a field of study that gives computers the ability to learn without being explicitly programmed. Over time, we've redefined and refined what machine learning means, and what we've come up with today is this. A computer program is meant to learn from experience E with respect to some class of tasks T, and performance measure P if its performance at tasks in T as measured by P improves with experience E. So a very convoluted definition, but essentially restating what Arthur Samuel said in 1959. Okay, so that's machine learning defined as a field. Now I want to define some key elements within machine learning. First, we have an algorithm, a set of rules or processes that is used to learn patterns from data. Algorithms are everywhere. Even we as humans use them. For example, when we're communicating, when we're thinking about how to form sentences, how to conjugate verbs, etc., we're all following an algorithm in our minds. An example of an algorithm in healthcare is a physician using a series of steps when performing a surgery. Step 1, disinfect the incision area. Step 2, make the incision. Step 3, insert the catheter, and so on and so forth. The next thing I want to define is a model. A model is the expression of an ML algorithm after it has been applied to data, or trained. So talking about the surgery example, a model might be the expression of the surgery algorithm after it has been fed in data on patient outcomes, previous complications during the surgery, and many other related things. We also have a predictor variable. Predictor variable refers to features in the data that can be used to predict results from testing data. These features might be, for example, when you're looking at an EKG signal for heart rate, the distinct peaks that show up. Then we have the response variable. The response variable is the specific feature that needs to be predicted using the predictor variable. So with the EKG signal, this might be, for example, whether it indicates a pathology or not. There's also training data, which is the data that the model is built off of, and testing data, which is the data that the model is evaluated using. So this could be EKG data from a group of patients, which is then applied to the EKG of a new patient. Having defined all these basic terms, I now want to talk about the machine learning process. Broadly, the goal of the process is to build a predictive model to find solutions to a given problem. There are 7 key steps in this process, which I will discuss in order. The first is defining the objective of the problem, kind of like a research question. So I'll stick with the EKG example throughout this video. A problem statement for EKG might be predicting the possibility of heart disease using EKG patterns. Some questions we might want to ask while generating this problem statement are, for example, what are we trying to predict? What are the features we want to target? What kind of data is going to be inputted? And what kind of machine learning do we want to perform, i.e. binary classification or more of a regression task? These names might seem a little foreign to you, but I'll be diving into each one of them in later videos. The second is gathering the data we need to solve the problem. So for our EKG situation, these will be EKG recordings from previous patients, as well as data on any physiologically related factors we might find important, like arterial blood pressure, intracranial pressure, and so on. The third step is preparing the data, also known as pre-processing. So we can't just take our raw data and throw it into the algorithm. The raw data is going to have a lot of issues that we need to clean up, like missing values, unnecessary labels, redundant values, and so on. We want to transform the data into a desired format. So this diagram shows some of the ways you can do that. Some of the terms here might seem a little complicated, but I'll be discussing them again later on. Once the data is clean, we can move on to doing some exploratory data analysis. At this point, we're not trying to immediately proceed with feeding the data into the model. Rather, we're just trying to understand the patterns and trends that exist within it. So this is the stage in which we're trying to draw insights and identify some of the correlations that may exist between variables. With the EKG signal, we might be able to identify that it has these distinct peaks, troughs, and notches, and then we can say based on that waveform, oh, we think this signal is indicative of a pathology, or no, it's not. This diagram has kind of a lot of complex terms in it as well, but the important thing is that it shows the overall flow of exploratory data analysis. Next step, I know this is what you guys have all been so excited for, is building the model itself. Okay, so this is where we take our pre-processed data, the training data, and apply a machine learning algorithm to it. So this could be something like a linear regression, an algorithm where it is assumed that there's a linear relationship between the predictive and response variables, or it could be something like a decision tree, where the algorithm will follow binary decision paths based on the data that it is fed. Then we have model evaluation and optimization. This is the stage where we use the test dataset to evaluate the efficiency of the model, i.e., how do the model predictions, pathologic or not pathologic in the EKG case, compare to the true condition of the patient. Here we want to calculate metrics like accuracy, precision, and recall, which I will again talk more about later on. Finally, after a lot of fine-tuning of model parameters and maybe modifying the data we're feeding in to maximize the accuracy of the model, we perform the predictions. This trained model can then be implemented in the hospital as an automated decision-making tool that helps physicians. So that's an overview of the machine learning process. So I also want to talk a little bit more about the different types of machine learning. So first, there's supervised learning. Supervised learning is where we have well-labeled data. So in the EKG situation, this would be like having all of our signals that we're training the model off of labeled as pathological or not pathological. On the other hand, we have unsupervised learning. So in this case, we would not have those pathological or not pathological labels on the EKG signal. Instead, the model would have to discover patterns and create its own labels, maybe based on the morphology of the signal, for example. So here I have a table that shows all the differences between supervised and unsupervised learning. First, the type of data. As I already mentioned, in supervised learning, the machine learns by using labeled data, while in unsupervised learning, the machine is trained on unlabeled data. The types of problems that supervised learning is used to tackle are more regression and classification problems, like finding the mean value of an EKG signal over an interval, or predicting pathological or not pathological. Unsupervised learning can be used for more association and clustering type tasks, where we want to group data according to certain features it has in common. This is particularly useful in medical images, where we want to characterize, for example, clusters of white matter in the brain. And then for training, it's external supervision and no supervision. For supervised learning, the approach is to tie a labeled input to a known output. In unsupervised learning, the approach is to understand patterns inherent to the data and discover outputs based on that. Some popular supervised learning algorithms include linear regression, logistic regression, support vector machines, and the k-nearest neighbors algorithm. Some popular unsupervised learning algorithms include k and c-means clustering. So here are some terms I already talked about before. I just want to make them clear for you now. So in regression, a form of supervised learning, the output is a continuous rather than discrete quantity. The main goal is to predict or forecast. Then we have classification, which is also a form of supervised learning, but in this case, the output is discrete, i.e., yes or no. The main goal is to compute which category any given data point belongs to. Then we have clustering, which is a form of unsupervised learning, and it arranges data points into clusters, with the main goal being to group similar data points together. So that brings us to the end of this introduction to ML. Again, the goal was to give you a big picture overview of what machine learning is as a field. And in the next video, we'll actually be getting our hands wet and doing a little bit of coding